get into this, see if we can solve some of these problems. I'm going to try to ask you some questions along the way, because I know you have worked really hard on these problems. But if we take a look at the first one, so let's see, we can start with the David Klein way of doing things, right? You're starting it with 6 carbons and you end up with 6, 7, 8, 9 carbons. So you need to add, these 3 carbons have to be added outside of the ring, and they're added on a double bond. Does anybody, know what kind of reaction you would use to make this double bond here? We want to make an alkene. Anybody? What reaction would you use to make an alkene? Give you a clue. It's a reaction that we covered in this chapter. All right, I'm thinking of a Wittig reaction, right? Thanks, Avisha. Yeah, I'm thinking about a Wittig reaction, right? Because if we had, let me just write it here in blue. If we had this ketone, cyclohexanone, and we reacted it with the appropriate green Wittig reagent, we could do the synthesis of this alkene. And so if you're wondering, like, how do I make the right alkene? Like, how do I choose the right number of carbons? Here's what you do. You look at both carbons in the double bond. So I'll highlight this carbon in red and this carbon in blue. So the carbon in blue, that's going to be the part that's going to be our Wittig reagent, right? Because the part in red has our carbonyl on it. So it's got a total of 1, 2, 3 carbons. So here's what we do. We're going to write 1, 2, 3 carbons like this. Okay. And then you make a double bond off the last carbon, and then you put triphenylphosphine on it there. I kind of ran out of space, but that is how you make your Wittig reagent. And of course, that's the ylene form, and you could draw it as the ylid if that helps you with your, with your rationale. You could draw it this way. There's nothing wrong with it. But after looking at our textbook a little bit over the past couple of days, I think he draws it in the ylene form a lot. And so now the question becomes, how do we get from here to here? How do we go from this cyclohexene to this cyclohexanone? And before we get into that, let me just address one thing about a Wittig reagent. Let me pretty this up here a little bit. So this is our triphenylphosphine. Okay, you can assume if it's a small Wittig reagent like this, you can assume that you have this. Assume this is available. Okay, you can just go to the cupboard, and if it's something that's got just 4 or 5 carbons in it, 3, 2, 1, whatever, something that's small, you can assume that you have that reagent at your disposal. Okay, so we're just going to go to the cupboard and grab that Wittig reagent. So again, let's get back to how do we get from here to here. If I want to go from cyclohexene to cyclohexanone, now it takes a few steps, but could anybody give me, it's going to take, a few steps to get there, but could anybody give me an idea about where to start here? What's the first thing you would do? Exactly. Heck yeah. Great answer, everybody. So what my students are saying, and let me just make a line here so we can see that this is a different problem down here. What my students all said is they said, Mr. Dion, just do this. Just take the starting material and treat it with aqueous acid, right? Because there's no Markovnikov or anti-Markovnikov, and that way we can make cyclohexanol, and then we can convert that to cyclohexanone using any oxidizing agent we want under the sun. Really, every single thing we learned, whether it's Des-Martin, whether it's Swern, PCC, chromic acid, use whatever you want. I know that my students really like PCC because it's fast, right? It's fast to write that down. I would totally accept that because it's right. And then we just have to choose the Wittig reagent. So we're going to put our Wittig reagent. So remember, the Wittig reagent has what? 1, 2, 3 carbons in it, and we put the double bond between the phosphorus and the carbon. And there you go. That's the whole synthesis outlined for this reaction. So this is 19.69A. Let's move on to 19.69B. So here we're making this compound on the top right of your screen. Could anybody tell me what functional group is found in this compound? And it's not a trick. I'm just making sure you know. Yeah, exactly. Thanks, Tiana. It's an acetal, isn't it? So if we want to make an acetal, so acetal, what is an acetal going to come from? This acetal is going to come from a ketone, right? And the ketone it's going to come from is this ketone right here. So you could call this cyclohexyl methyl ketone. Anyhow, the name's neither here nor there. But if we have this ketone, we can just treat it with a catalytic amount of acid, methanol, remove water, and that's going to give us this methyl acetal, if you will. And so now the question becomes, well, how do I get from here to here? Let me ask you a question before we get into this part of the synthesis, getting from this geminal dibromide to the ketone. Anytime you have, so do you guys remember the word geminal? Geminal means like Gemini twins. You got two groups that are identical on the same carbon. So we call this a geminal dibromide. Now, go back into all the reactions you've ever learned in this class. You've only ever learned one possible reaction that you can do with a geminal dibromide. Could anybody tell me what it is? Or what you would do with this geminal dibromide? Exactly. Exactly. You're going to hit it with excess sodium amide. Thank you. Everybody got that one correct, right? So excess sodium amide, right? And that's our first step. Right? And then we're going to treat it with H2O. And if you wrote H3O plus, that's fine too. I don't care. You could write either one and it's acceptable to me. And could you tell me what functional group that's going to make? I know you know, but just go over it. Exactly. That's going to make an alkyne. So you're going to have a terminal alkyne. Now, if you're really astute with your reactions, you would know that you can go from a terminal alkyne to a methyl ketone in one step. Does anybody, thanks Nicole, perfect. Does anybody remember the reagent that you need here? It's sulfuric acid, water, and there's one special one. Yes, exactly. Perfect. You guys are faster than me, right? It's sulfuric acid, water, and like Audrey said, it's mercuric sulfate, right? That's what spruces up the reaction and gives you the methyl ketone. Remember, this is a Markov-Nikov addition. Right, this is just a regular old Markov-Nikov addition, which actually gives us an enol. If you want to practice, we could draw the enol. So the enol would look like this, but then the enol undergoes tautomerization to give you the carbonyl or to give you the ketone because it's more stable. And so our last step is a reaction we learned in this chapter. So we would treat this with methanol, and you could put two equivalents of methanol, or if you wrote excess methanol, that's totally fine. A catalytic amount of acid, and then removal of water. In hot dog, we have a wiener. That's the whole reaction right there, the whole kit and caboodle. All right, let's move on to the next one, and I'll try to stop saying, funny things like that. All right, so let's see here. Again, this is 19.69 from Klein 4th edition. Let's see here. Audrey, what do you smell? Or this one, what? Last time you said, I smell a reaction, and you were right. Obviously we're doing a ring expansion here, right? Yeah, yeah, exactly. Because here we have 5 carbons, and then here we have 1, 2, 3, 4, 5 carbons, right? But then we have, 6, 7, and 8. So you're adding 3 carbons. But like Audrey said last class or a couple classes ago, Audrey said, I smell ozonolysis. It's funny you said that because ozone has a very distinct odor. Anyhow, but yes, we definitely need to do an ozonolysis here. Anyhow, so we got that in our hat, right? We know we need to do a reaction with ozone. And before I get to that, can I just ask you guys a question? See this compound here, and we don't deal with a lot of 8-membered rings in this class, but there's 8 atoms in that ring. What functional group is in this compound? And it's not a trick. Mr. Dion detests that. I know I say that 10 times every class. Yes, exactly. This is an acetal, isn't it? And so if you understand, maybe I'll scribble it up here. Yes, absolutely. It's a beautiful acetal, isn't it? Right. And if you do a little retrosynthesis here, you'd say, well, this acetal, this part comes from, oops, I can draw it a little prettier than that. It comes from acetone, which is this compound. Okay. And then the other part of it, the part with the 5 carbons, comes from this. Look, you got 1, 2, 3, 4, 5, and then you have a hydroxyl here, and then you have a hydroxyl here. That's how you would make this compound. So now the question becomes, right, Audrey, how do we get from here to here? Right? And she said, well, you're going to start with ozone. Let me scribble this in here. So step 1 is ozone. Step 2 is DMS. Break that ring, right? Crack that sucker open, right? So let's see here. 1, 2, 3, 4, 5. And then here we're going to have an aldehyde. And here we've got another aldehyde. All right. What do you got? Lay it on me. What do you want to do to reduce those aldehydes down to an alcohol? Give me a reagent. So remember, this is a reduction, right? If we want to reduce it, yeah, exactly. Thanks, Avishi. Perfect. I'd say LAH or sodium borohydride. In my notes, I wrote sodium borohydride, but Avishi wins. So we'll put here LAH, yes. And then in here in the second step, again, Mr. Dion doesn't care. I would accept water or acid. Either one's fine with me. Let's just put aqueous acid this time. Oh, hell. Let's put both. Okay. Both are totally fine. So you'd have 1, 2, 3, 4, 5. There you go. That's your diol done. And then to make the acetal, all we do is we treat it with acetone. So our ketone, we need a catalytic amount of acid. And we remove the water. And there you go. That's the whole thing. I won't ask you to give me a thumbs up, but let me ask you, do you have any questions about any of these problems in 19.69? I'm going to assume that most people looked at the solutions manual. I would have. You know, after I worked really hard on the problem, I always check my answers. All right. If there's any questions, do not hesitate to interrupt me, okay? Do not hesitate. This is the land of the free. All right. There we go. Good. Anybody try 19.73? Huh? Huh? Anybody do this one? All right. Awesome. Awesome. Okay. Perfect. Remember, Mr. Dion's classroom, like I've told you before, this is not a joke. My classroom is a safe space. If you have a question, you ask it, okay? So if you have a question on any of these, because in this one, we go back into some of our older reactions, right? There's a few things that show up here that we haven't maybe thought about in a couple of weeks. So let's take a look here. I'll ask my students again, what functional group do we see in this molecule? And again, I know you know, but I just want to check. Yes, thanks, Maria. Absolutely, it's an acetal, isn't it? So Maria probably did. Actually, I'm positive that Maria would have done a retrosynthesis like this, where Maria would have said, "Well, you've got a cis diol, and then the aldehyde you would have reacted it with would have been formaldehyde, right? That's what you would have made it from." So if you can do this retrosynthesis, I'm pretty sure that everybody who's hearing the sound of my voice can do this part in their sleep. Okay, how do you make a cis diol? Anybody? If I want to take this compound and make a cis diol, that arrow wasn't very good, but oops. I'm just writing here on my iPad, so I'll look up at the chat. Anybody have an idea? How do you make a cis diol? Anybody remember? Yes, absolutely. Thanks, Deanna. Osmium tetroxide. And a catalytic amount of NMO. If you just write NMO, that's good. If you wrote NMO, catalytic, I don't care. It's all good. Yes, Audrey, that would work too, wouldn't it? Right, to do the potassium permanganate method as well. That totally works. Yes, either one. I would even accept those weird methods that he put in the book. What were they? Osmium tetroxide and then sodium bisulfite or something for the second step. Those are fine too. You know, we learned a bunch of different ways to do this reaction. Yes, we make a cis diol, and then in the next part, we just treat it with formaldehyde. So we'd use formaldehyde, a catalytic amount of acid, and of course, you want to remove water. I don't know. Did anybody here Google this thing here called the Dean Stark trap? If you want to know how the water is removed, I don't have the time to explain it right now, but it's using it's just a piece of glassware that you can buy. It's called a Dean Stark trap, and it's a pretty clever invention. I'll tell you what. If you come to my office in the fall and you're like, "How does that thing work?" I'll explain it to you, because I have to act it out with my hands maybe a little bit. All right, let's try. Noted. Yeah, stop by anytime, Audrey. Door's always open. All right. If I just by the way, if you've never had me as an instructor before, you know, I do have regular office hours, but my policy is if the door is open, you know, I'm always willing to chat unless I'm in a meeting or something. And I'm usually looking for a reason to get out of a meeting. I can't believe I'm going to put this on YouTube, but anyhow. All right, so let's take a look at the next problem here. So we're starting it with a compound with 8 carbons. 8 carbons, so 6, 7, 9, 10, and then we've got 11 carbons. So you can see that we're adding these 3 carbons here. It's kind of an interesting reaction, this one here. I mean, the disconnection, the first disconnection that I would make is a Wittig reaction. Wittig reaction, yes. If I could make this compound, so 1, 2, 3, 4, if I could make this carbonyl, then I could just treat it with this Vidig reagent. I'm kind of running out of space here, but that would put in that methylene, right? This is called a methylene, right? CH2 is a methylene. So that would install that. So then the question becomes, well, how do I make that? I'm starting to delete stuff that I didn't want to. How do I make this carbonyl compound? And, really you need to add these two carbons, right? And so you could do that from, you could do that. Could anybody make a suggestion here? Because I'm kind of revealing. Yes, Tiana. I look up and there's the answer, right? I would make it from a green yard, right? So if you're wondering, what Tiana is saying is if you had a green yard, so you treat this with magnesium, right, to make this reagent here, then your electrophile would be this molecule here. If you remember, this is called acetaldehyde, and that would make the alcohol, and then you could just oxidize the alcohol with PCC or SWERN or whatever. So yes, Tiana, that's how I would do this, is with a Grignard reaction. So let's just write down the first few steps because we kind of did it already. We said magnesium to make the Grignard, and then acetaldehyde to make the alcohol, and then 3, of course, you need a source of protons, so we'll put H3O plus. And I haven't drawn this, but the molecule you would get would be this. So 1, 2, 3, there we go. So we'd end up with this alcohol. Somebody says, could you also add a terminal alkyne? Yeah, so Jaylin, I'm gonna go down to a blank page in a second. I'll address your question. It's a good one. And I think you've got as the French say, you have reason. All right, so French we say "t'as raison," which means you have reason, literally. Anyhow, so let's see here. I'm getting ahead of myself here. Okay, so we have our carbonyl, and then we'll do our Grignard, our Vidig. Getting my name reactions mixed up today. Okay, so what Chaylin said is, let me just go down here to some blank space. So Chaylin says, well, what if you just did this? I don't know. Did anybody look at the solutions manual? Because I did not. No idea what it says. But I like the way you think, Jalen. I think this is a pretty neat way of doing it. So all Jalen is saying is that you get an SN2 here, right? Nucleophilic attack, loss of leaving group, and you end up with 1. Oops, where's my black pen? You end up with 1, 2, and then 3, and 4, and then then you'd make the methyl ketone. Is that what you were suggesting? Right on. Yep, I agree with you, Jalen. I think that's reasonable. So 1, 2, 3, 4, and then you would have this. Then you do the Vidig. Yep, I would accept either one. They're both reasonable to me. Does anybody know what the solutions manual says? I don't even have mine open in my shelf. The solutions manual has what you've done plus BCC and dichloromethane. Did I leave that step out or something? Well, I'll have to go back. Anyhow, so yes, I would accept this. There's nothing wrong with that synthesis. So what did I do? Yeah, so the PCC, yeah, you can use dichloromethane as a solvent. You can use chloroform as a solvent. But yeah, so dichloromethane would be a good solvent for sure. All righty, so let's see. The first one, 1, 2, 3, 4, 5. This method is 1, 2, 3. Yeah, I don't see a reason why this wouldn't work. All right. Good work, Jalen. I think that's perfectly fine. I don't know what happened in C. It seems like I lost part of my final product here or something. Anyhow, so let's fix this up here. Let me just maybe I'll copy this and move it to where we have some more room. Son of a gun, what am I doing here? Striking out here. Try this. Copy. I'll paste it down. Anybody do this one? C? Anyone? Nobody? Okay. All right. Well, what would be the first reaction? What's the only possibility for the first reaction? Hot diggity dog. Yes, bromine and light. Yes, that's the only possible answer, right? So if we scribble that down, There are two CHEM dimethyls. Then we'll have a bromine here. Okay. Let's do a little retrosynthesis too. What functional group do we have here? Yeah, heck yeah, it's an acetal, isn't it, right? So that means it's going to come from this. Let me try and draw it neatly here. It's going to come from this aldehyde and from this diol, which is ethylene glycol. So then the question is, well, how do we get from here to here? Well, we know that the aldehyde, there's no change to the carbon skeleton here, so it must come from an alcohol, right? It would have to come from the primary alcohol. So if we draw this like this, okay? And then the primary alcohol, that could come from the alkene, the exocyclic alkene. So exocyclic is just a fancy word for the double bond comes off of the ring, although that looks terrible. So I'll fix it up here. There we go. That's a little prettier like that. All right, so now we've simplified the problem greatly. How do we get from here to here? Well, if we look at this bromine, there's only one type of beta proton in the entire molecule, and it's this one here. And so we have a tertiary alkyl halide, so really it doesn't matter what base we use. We're going to end up getting an elimination reaction. Did anybody choose a base for this reaction? I have something written down in my notes. I mean, you don't have to be that fussy here, really. You can use sodium methoxide, and that will work. Yeah, potassium T-butoxide, that'll work too. Yeah, I'd pick either of those. Again, just about anything will work here because you're not going to get any substitution. So my students really like T-butoxide, so let's throw that in. There we go, and that's going to give us the alkene like this. There we go. And then to make the alcohol, we're going to do an anti-Markovnikov addition. So for that, we need borane and THF, followed by hydrogen peroxide and sodium hydroxide. That gives me the alcohol. Am I going to run out of space here? Go. So we get the alcohol. Maybe I'll just kind of cram all the last steps together. Get here. So step one is going to be PCC, PCC. PPC is People's Party of Canada, but PCC is pyridinium chlorochromate, right? Anyhow, step two is going to be ethylene glycol, and then H plus, so our acid catalyst, and then loss of water, and that's it. There we go. We did quite a bit of retrosynthesis on that one, but I guess seemed to be pertinent at the time. Oh, we haven't talked about imines or enamines. Let's do a little something with that for a change here. So let's see here. This is 19.69. Or sorry, this is 19.73. My mistake. 19.73. I wanted to try E. So E, and I'm sure you can all nail this one pretty quickly, but let's just go over it quickly. So you're starting with methyl cyclohexane, and you want to make this compound. Hydrogen here. So can anybody remember the name of this functional group here? This guy? Excuse me. It's an imine. Thanks, Tiana. Exactly. It's not an enamine. This one's an imine or Schiff base. Yes, either one. Right, the Schiff base. And Schiff bases are great because you can do a really tasty retrosynthesis with them very quickly, that you need this carbonyl compound. And in this case, what would be our amine? Can anybody name it? I know we haven't covered amines, but I think you could name the amine that you would need in this case. In fact, I know you can name it. What would be the amine you would need? You would need ammonia in this case. All right, you need ammonia in this case. Okay, thanks, Audrey. Perfect. So then the question becomes, well, how do we get from here to here? If we lose a carbon, right, because here we've got 7 carbons, and here we've got 6 carbons, you can see that the retrosynthesis must involve methylene cyclohexene and then doing an ozonolysis. Right, and I know that if I asked you guys what's the only reaction you can do here, you would say this, bromination, right? And so if we do that, there's two types of beta protons. You have these ones in red. You have these types in blue. You want to pull off the red ones, so you'd use a hindered non-nucleophilic base. And so you could use really, am I doing this wrong? Am I missing a group? I made a mistake. Mr. Dion made a mistake. There's supposed to be a methyl group here on the product. Nobody interrupted me, so let me. I'll put this here. That's still okay. So let me just erase some of this. So there's supposed to be a methyl group here, and there's supposed to be a methyl group there. All right. So if I want to pull off the blue proton, because I want to make the Zaitsev, yes, there we go. I would treat it with sodium ethoxide, wouldn't I? There we go. Now we're getting off the garden path, so to speak, because we need to make this compound. And then from here, we need to get to here, right? So in order to do that, we're going to have to make the, sorry, we're not going to have to make this compound. No, we don't have to do this. We're going to have to make the alcohol here, aren't we? Okay, there. I fixed my retrosynthesis. It's much better now. So if I want to go from here to here, do I want to do an anti-Markovnikov addition of water or a Markovnikov? We'll fix it up that way. What would it be here? Yes, thanks, Audrey. It's anti-Markovnikov. Wonderful. So let's just do a little anti-Markovnikov something here. So first step is going to be boron and THF, followed by H2O2 and sodium hydroxide. There, now we're back on track. Good. Okay, so now we've got this compound. If we want to oxidize it to the ketone, we're going to treat it with PCC or whatever. We could do a Swern, we could do desmartin periodinane, that will work. And then to make this compound, we're going to treat it with a catalytic amount of acid. Ammonia is going to be our amine, and then the loss of water to make the imine. All right, I really botched that one because I lost a methyl group, but that shows you if you lose one carbon, how you can get sidetracked pretty quickly. That one's something I know you all know how to do. So let's try something else here. Let's try this one. This is 19.73 G. So 19.73, this is G. And I think this is a good problem because it involves electrophilic aromatic substitution. And that's something we need to consider. All right, so if I want to make this compound, let me fix that. There we go. Could anybody tell me what functional group is in the final compound and not the aromatic ring? I don't care about that. Could anybody tell me what functional group is in here? Yes, thanks, Avishi. It's an enamine. We haven't talked about those today. So enamine, yes. And so if I wanted to make this enamine, what's that going to come from? Now, you've got to be really good at your retrosynthesis, but we practiced this last class a little bit, and we said the amine that this would come from would be acetophenone, right? And then all you have to do is treat it with dimethylamine, catalytic amount of acid, and remove water. So then the question becomes, well, how do I get from here to here? From the aromatic ring, from benzene to acetophenone. Can anybody tell me how to do that? You can do it in one step. All right. Friedel-Crafts, what is it, Tiana? Acylation, right? Not alkylation. And so to do that, you would use the acid chloride, right? You use, this is called acetyl chloride or acetyl chloride, depending on who you are, how you pronounce it. So acetyl chloride, yes. And just, I'll write this down here in case anybody needs to look it up. So this is Friedel-Crafts acylation. We covered this in chapter 18, okay? And I know you're studying that chapter hard, so you probably have that down pat, but just in case. So we'll scribble all that down. We put it in our acetyl group, and that brings us to our very last step. So we're going to treat it with dimethylamine, okay, a catalytic amount of acid, and then the loss of water. So we remove water using the special distillation technique, the Dean Stark apparatus. You know, there is another way besides a Dean Stark to remove water, and that's using something, this is no joke, it's called a molecular sieve, okay? It's like a diatomaceous earth, and it will absorb water, but it won't absorb other small molecules. So That's another possibility. Anyhow, let's see here. Want to do one more? Let's try 19.73H. So 19.73, and this is H. And again, this is from Klein, 4th edition. This one's a interesting reactions or interesting synthesis, maybe. See here if I can make this line a little straighter. There we go. So we have this dialkyne, and then we're taking that, and then we want to make this giant compound here, or what looks like a big compound. Anyhow, so we've got a methyl group here, 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 and here. Okay. So you know what? If I was a student, just learning the subject, I might look at this problem and say, what is going on here? Like this thing's kind of tricky. If you count the carbons, so we've got 1, 2, 3, 4, 5, 6, 7. Here we've got 1, 2, 3, 4, 5, 6, 7. I kind of counted them in a weird way. Here, maybe I should have done it like this. Maybe I should have done it like 1, 2, 3, 4, 5, 6, 7. That might make more sense. And so we're only adding one carbon. And again, this is not a trick question. Can anybody tell me what functional group is found in this compound? Yeah, it's an acetal. Thanks, Jalen. Yeah, it's got an acetal in it. Acetal. Yes, if it's got an acetal, then we could do a quick retrosynthesis. Oops. And we could say it must come from this diol. So there we go. So it must come from this diol. And then you'd also need formaldehyde, right? That would be your carbonyl compound. All right. And so then the question becomes, well, how do we get from here to here? And you can see that both of those compounds have a total of 7 carbons. And so, we could think of this compound, this diol, is coming from the diketone, couldn't we? Right? We could think of this as coming from this compound. Right? And all we'd have to do is do a double reduction. What was the word? What was your favorite word? Sorry, I forget what I say very quickly. Anyhow, acetal? Oh, maybe. All right. Anyhow, yeah. So where were we? All right. So now we need to go from here to here. Anybody want to help me out with this one? There's a quick way of doing this. So this one, you don't want to do an anti-Markovnikov in this case, right, Avicii? Because you want to add that's right, because you want to add the carbonyl here and here, right? So it has to be a Markovnikov in this case. That's right. Okay, so you got to look at it really carefully. I agree to kind of get that straightened out. So yes, you would treat it with mercuric sulfate and sulfuric acid and water. Yes, and that will give you that diketone. Zoink. There we go. Yeah, acetals do come up a lot, and just to give you a heads up, they come up a ton. So I'm going to use sodium borohydride for this reduction. I'll do it in methanol. If you did it in water, if you used LAH, I don't care. It's all good. They come up a lot in the carbohydrates chapter too. Acetals and hemiacetals both come up because an acetal, when you make an acetal of a carbohydrate, it makes what's called a glycoside. Anyhow, that's neither here nor there for today. So the last step is just going to take formaldehyde, catalytic amount of acid. I know you know this one, right? And then loss of water. We got to say it that way. And there you go. That's the whole thing. Now, to me, these are really good problems. I like this kind of problem for my students because I think it really forces you down and forces you to sit down and go over reaction after reaction after reaction. So I would really recommend, trying these problems again on your own. Maybe give it a day and probably forget a chunk of it, and then come back and give it another kick at the can.